On April 17, 2025, every major news outlet on Earth ran the same headline. A chemical linked to living organisms had been detected in the atmosphere of a planet 124 light-years away. A team at the University of Cambridge's Institute of Astronomy had used the James Webb Space Telescope's mid-infrared instrument to analyze the atmosphere of an exoplanet called K2-18b. What they found was the spectral fingerprint of dimethyl sulfide, or possibly dimethyl disulfide. On Earth, these two molecules are produced exclusively by living things. Marine phytoplankton and bacteria generate them in the oceans, and no known geological process replicates them. The team announced that the probability of this signal occurring by pure chance was just 0.3%. In other words, there was a 99.7% confidence that the molecules were genuinely present. The lead researcher stated that if the link to biology is real, this planet would be teeming with life. But 99.7% does not equal discovery. To qualify as a confirmed scientific finding, the result must reach 99.99994% certainty, a benchmark known as 5 sigma. Between 99.7 and 99.99994, a vast and treacherous gap remains. What truth is hiding inside that gap? K2-18b was first spotted in 2015 by NASA's Kepler Space Telescope. It sits in the direction of the constellation Leo, roughly 124 light-years from Earth. In kilometers, that is about 1,173 trillion, a distance that even the fastest spacecraft ever built would need millions of years to cross. The planet is classified as a super-Earth or sub-Neptune, with a mass about 8.6 times that of Earth, and a radius roughly 2.6 times larger. It completes one orbit around its host star every 33 days, at a distance of about 21.4 million kilometers. That host star, K2-18, is a red dwarf far smaller and cooler than the Sun, but because K2-18b orbits so close, its surface temperature falls within the range, where liquid water can exist. It sits squarely inside the habitable zone. In 2023, the same Cambridge team used 2 near-infrared instruments on the Webb telescope to take the first detailed look at this planet's atmosphere. They detected clear signatures of methane and carbon dioxide, while ammonia was notably absent. That specific combination suggested a massive liquid ocean might exist beneath the atmosphere, absorbing the ammonia. The researchers proposed that K2-18b could be a Hycean world, a planet entirely covered in water beneath a hydrogen-rich atmosphere. 2 years later, a second round of observations using an entirely different wavelength range produced the result that changed everything. The Webb telescope studies exoplanet atmospheres through a technique called transit spectroscopy, when a planet passes in front of its host star. As seen from Earth, a sliver of starlight filters through its atmosphere. Different molecules absorb different wavelengths, leaving a chemical fingerprint in the spectrum. During the 2023 observations, 2 near-infrared instruments captured clear signs of methane and carbon dioxide. A faint hint of dimethyl sulfide also appeared, but the signal was too weak to confirm. That trace was enough to justify a second look. In 2025, the team observed K2-18b again, this time with the mid-infrared instrument covering a completely different wavelength range with 0 overlap. The result was striking. A strong, clear signal consistent with dimethyl sulfide or dimethyl disulfide emerged from the data. Because the 2 molecules belong to the same chemical family, their spectral signatures overlap, making it impossible to distinguish which one is present, but at least one of them clearly was. What made the finding even more remarkable was the estimated concentration. On Earth, dimethyl sulfide exists in the atmosphere, at less than 1 part per billion by volume. On K2-18b, the estimated abundance was thousands of times higher. If this is biological in origin, the ocean of K2-18b would need to sustain biological activity, far more intense than anything found in Earth's seas. The team published the results in the Astrophysical Journal Letters. The first twist concerns the identity of the planet itself. The Cambridge team argues that K2-18b is a Hycean world, its entire surface covered in liquid water beneath a hydrogen-rich atmosphere. They explain the absence of ammonia by proposing that a vast ocean absorbs it. But other teams analyzing the exact same data reached radically different conclusions. Some researchers contend that K2-18b is not an ocean world at all, but a lava planet, its surface blanketed in molten rock under a thick hydrogen envelope. Under this interpretation, the missing ammonia is explained by extreme temperatures, not water absorption. If this is correct, K2-18b is a hellscape where life cannot exist. A third group suggests the planet may be a mini-Neptune, a gas-dominated world with no solid or liquid surface whatsoever. One planet, three mutually exclusive interpretations. Ocean world, lava world, gas world. A renowned astrophysicist at MIT framed the challenge bluntly. Everything known about exoplanets comes from the minuscule amount of light grazing their atmospheres. Reading that faint signal to determine not just whether life exists, but even the basic structure of the planet is an extraordinary challenge. She warned that the Biosignature candidate could remain in candidate status indefinitely. So what exactly does 99.7% tell us? The mystery lives inside the numbers. 3 sigma, or 99.7% confidence, sounds overwhelming in everyday life. But in science, a new discovery must reach 5 sigma, meaning 99.999994% certainty, a less than 3 in a million chance the result is a fluke. The gap between 3 and 5 sigma is not just numerical. History is littered with 3 sigma detections that vanished. When more data arrived, the team estimated that 16 to 24 additional hours of Webb observation time would be needed to close the gap. But even before that could happen, the pushback began. In late April 2025, an independent group reanalyzed the same dataset and concluded the dimethyl sulfide signal was not robust. By July, a NASA-led team published its own analysis, finding no conclusive evidence for the molecule. They reported that 87.5% of their retrieval scenarios failed to detect it. The key issue was that different data reduction methods and baseline models produced wildly different outcomes. There was also a chemical puzzle. If dimethyl sulfide truly exists in that atmosphere, ultraviolet radiation from the host star should break it apart, producing ethane as a byproduct. But ethane was not detected. The biosignature gas is present, yet its expected byproduct is missing. Is this a limitation of the instruments, or evidence that the gas was never there at all? The second twist extends far beyond a single planet. More than 5,000 exoplanets have been confirmed to date. Hundreds sit within the habitable zones of their stars. Yet only a handful have atmospheres detailed enough to analyze. And K2-18b is effectively the first where a biosignature candidate has been detected. The lead researcher framed the stakes in sweeping terms. If life is confirmed on K2-18b, it would mean life is very common across the galaxy. In an infinite universe, even one example opens the door to countless others. The statistics reinforce that logic. Our galaxy alone contains an estimated 100 to 400 billion stars, and roughly 20% are believed to host at least one planet in the habitable zone. If a single biosignature is confirmed, tens of billions of life-bearing worlds become a plausible inference. But a leading astronomer at the University of Edinburgh offered the opposite perspective. Even with 5 sigma certainty that the gas exists, that would not prove a biological origin. On Earth, only living organisms produce these molecules. But on an alien world, unknown geological processes could generate the same chemicals. Strange things happen in the universe, and declaring life based on one molecule is premature. The Cambridge team acknowledged this possibility and revealed they are collaborating with laboratory researchers to test whether dimethyl sulfide can be produced through non-biological means under conditions mimicking K2-18b's environment. Here's what can be stated with certainty right now. In the atmosphere of K2-18b, 124 light-years away, molecules known on Earth to be produced only by living organisms were detected at 99.7% confidence. The estimated concentration is thousands of times higher than on Earth. Whether this planet is an ocean world, a lava world, or a gas world remains unresolved. Independent teams analyzing the same data have challenged the very existence of the signal. Reaching the 5 sigma threshold required for a confirmed discovery will demand 16 to 24 hours of additional Webb observations, and the research team believes this can be achieved within 1 to 2 years. That is exactly where humanity now stands on the boundary, between discovery and doubt, between life and lifelessness, between certainty and suspicion. The lead researcher left one final thought. Decades from now, we may look back at this moment and recognize it as the point when a living universe came within reach. But before that, he said, a harder question must be asked. Whether humanity is truly prepared to encounter life in a form it has never imagined. Beyond 124 light-years, a blue world circling a red star every 33 days is still waiting for an answer.